Hello, everyone. Welcome to join the Tech Talk in Edinburgh PM team. Today we invite our intern, Todd Ambridge, which is a PhD student from the University of Birmingham, to give us a tech talk on the global optimizations while constructive real numbers. Yeah, so Todd, maybe you can also give yourself a brief introduction to everyone.
Yeah, so as Tilla said, I'm a PhD student at University of Birmingham under Dan Geeker. I'm in my third year, and I've been looking at various applications of constructive real number, the theory behind constructive real numbers, the applications of that towards things like machine learning, regression analysis, and things like this. So that's what I'll talk a little bit about today. My talk here, I mean, this is a Thursday tech talk. This is probably a bit less technical than some of the other talks. It's more like an overview of the area and a tutorial into that, just sort of to get everyone onto the same page. And then I'll talk a little bit about my application towards the end. Hopefully there'll be nothing too technical, but if you have any questions, just feel free to interrupt and ask at any point. So what I'm going to do is sort of introduce this area of convergent global optimization, discuss how floating point real numbers aren't really an appropriate data type for this, then introduce two types for arbitrary precision real numbers or constructive real numbers, and show how one of these types allows us to define this kind of convergent global optimization that we're discussing. And then finally, which is more related to research that I've been doing, is applying this framework to kind of an area of machine learning or foundational machine learning, which is regression analysis, and then how we can get convergent properties for regression analysis out of this convergent global optimization on a general wide variety of types that we call searchable types, which are from the literature as well. So the first kind of key thing that we say is, well, optimization is a core component of supervised machine learning, and you know, this has broad applications to curve fitting, function approximation algorithms in general. So interpolation, which is reconstructing a function by sampling it, and well, in linear interpolation, joining the dots, or in polynomial interpolation, finding a polynomial that fits this curve. Whereas regression is like we pick a model function with up to some parameters, and then we adjust the parameters to fit the curve. And optimization fits in everywhere in this kind of field, minimization, maximization, things like that. So the first sort of type of optimization algorithms are local ones, such as gradient descent, which is used throughout like deep learning, neural networks, things like this. And they've been studied extensively and basically made as efficient as they can be nowadays. But the sort of the other side of this, which is correctness, sort of global optimization algorithms, such as these branch and bound style algorithms, which some people may be familiar with, they're much less practically kind of available. But something that we do have that's interesting about them is that they never yielded an incorrect result. So there's a little bit of trade-off of like efficiency and correctness here, but really what we would like to get to is a point where we can have correct results efficiently as well. And so just to kind of illustrate these two processes, if we have a curve like this, which has two local minima, one global minima, with gradient descent, you know, you could end up here, or you could also end up here. And based on the size of these curves, okay, maybe you have like a 60% chance, depending on where you start, to get around here, a 40% chance to get around here. And maybe you're okay with those odds, and then you can do lots of tweaking, you can run the algorithm again, you can improve it, and you can increase the percentage chance that you'll find a better result. You can never really completely discard the chance that you may just get something wrong. And this is a very simple function, but with more complex functions, you know, this chance is just going to increase. Whereas if we look at a kind of global approach where we, and this is a branch and bound style approach, we say, okay, well, let's take an interval that we're searching in, and we bound the sort of range of the function by some kind of continuity procedure, such as its Lipschitz value, for example. And then we can sort of iteratively branch the function into we sort of partition the function, and then we bound it again. So now in this area, our estimates tell us, okay, we can never get better than this or worse than this. We're doing minimization here. And then we kind of say, okay, well, this looks more promising, so we're going to branch this again, and this still looks really promising, so we're going to branch this again, and now this area looks quite promising, so we're going to branch this, and then we get to this point here where if we look at these two candidates in the interval, the absolute worst case of this area is still better than the absolute best case of this area. And that means that we can just discard this as a candidate. So very quickly, we got to a point where we completely discarded this as a candidate. Whereas with the local approach, that never happened. There was still always a chance. Iteratively, we're going to zoom in onto this curve. And then eventually we're going to get to a point where, okay, maybe like a local approach, like we just return the best in this value is the best thing to do. But in the infinite, we can kind of zoom in more and more and more to the global optimum. The key fact here is that we never discard it. So as I was saying, with a local approach, we could end up here, or we could end up here. With a global approach, we're always going to zoom in eventually on the area. But this eventually is what puts people off. I mean, they worry about the efficiency of this. And so that's what we're going to discuss a little bit as well. So I'd say like gradient descent type algorithms, they're like finding local minima using the derivative of functions, whereas branch and bound style algorithms, they're using global minima using the continuity information about a function. And then we're going to think about the convergence of this. So how can we be sure that we are always going to eventually get this great result? And so first, just want to remind people a continuous function. So a continuous function comes equipped with a modulus of continuity function, such that, well, if we compute the modulus of continuity at a particular point relative to some other point, essentially what we get is, well, we pick an interval, here's our x, and then our distance is going to be the distance between the x and the edge of the interval. Yeah, and then this is going to bound the function values, and this is essentially what gives us our bounding process that we saw previously. So we take the center of the interval, we take the half the width of the interval, and then what we get is a maximum of the height of the interval, half the height of the interval. And this is what allows us to do this bounding process. If we have this modulus of continuity, we can perform this bounding process. And then we say, well, a global optimization approach, not just a branch and bound approach, but any global optimization approach is convergent if for any epsilon, we can compute the best value up to that epsilon. And what we essentially mean by this is that the maximum height of the total search area has decreased below that epsilon. And then at that point, we can just return the best result, but we've reduced ourselves into that area. And so a branch and bound style algorithm converges in this manner if, well, first the function's continuous, so that we can actually perform this approach. Secondly, whatever branching, the partitioning process ensures that the width of the widest box eventually tends to 0. So we have to know that the search area, the candidates are sort of getting smaller, and then the bounding procedure ensures that as the width of the box decreases, so too does its height. And we can see, using these first two approaches, this kind of ensures this as well. So basically, with these three criteria, what we get is an assurance that eventually the height of the entire search area is going to decrease below epsilon. And again, it's that word eventually. We don't know how long that is, but we can be sure that that's going to happen. So then we start thinking about, okay, well, let's implement this approach, and let's use our usual type of real numbers that we have in a programming language, which is floating point. When computer scientists talk about real numbers, they usually just use the word floating point numbers. When we're taught about floating point numbers in school, we call them real numbers. And this is for obvious reasons, I mean, representational reasons. But in this regard, in this particular instance, floats are an inappropriate data type for performing this type of global optimization, this type of convergent global optimization. And so the reason why is, well, we could think about kind of general floating point errors that everyone kind of understands. Like you have a basic C++ program like this, where you add to x 0.1 10 times, but you add 0.01 100 times. You expect the result to be 1 in x and 1 in y. And sure enough, x gives 1, but then y gives 0. Several number of 9s. And it's a bit confusing to see why this happens. But these aren't really the errors we're quite interested here. Everyone knows about these sort of errors, and there's many processes to go around hacking away ways to ensure that these don't happen. And these sort of errors do lead towards quite funny situations, and there's a lot looking into adversarial neural networks or adversarial machine learning nowadays, where you can use certain errors in your procedure. So for example, this uses floating point numerical error, like the one we just saw, to identify an aeroplane as a horse or a horse as a deer, which I don't think is that much of a difference really anyway, but this one is a lot more significant. So So everyone knows about these sort of errors, and we have ways of dealing with this. Indeed, this paper kind of concludes, well, we can perform this this assured sort of floating point computation to make sure that we don't lose track of these errors, to make sure that we know when an error has occurred. The type of errors that we're thinking about here with floating point are different. They're more like a Zeno paradox situation. So if I try and explain this illustratively, if you've heard of this problem where you have a car with a bird on top of it, and then eventually it sees another car, and what it's going to do is it's going to kind of ping pong between the two. And the question you're often asked is, what distance does the bird travel before it gets squished? And this is kind of like a Zeno situation, like I said, like the Achilles and the tortoise, if you've heard of that one. And so what we're going to do is the bird's going to fly between the cars, and the cars are going to get closer, and then it's going to turn around, and then it hits the other car, and it turns around again, and it turns around again, and it keeps doing this several number of times until it gets to this sort of infinitesimally small region. And as I say, the question you're usually asked is, how far does the bird travel? And it's the original area that it had is what it travels. But in this case, what we're asking is, how many times does it turn before it gets squished? And the answer to this is, it turns an infinite number of times before it gets squished, because it gets to a point where it's just basically spinning on the spot infinitely, and then it gets squished, apparently. Or it never gets squished, might be the Zeno way of saying it. But yeah, so it turns an infinite number of times. But if we put this into a floating point calculator, then it just sort of spits out, it turns 158 times, which we ask ourselves here, well, is 158 a good simulation of infinity? Is this really on the money of what we were trying to prove? And then, okay, we can use double precision, and maybe it gives a much higher number. Or maybe we try and keep track of errors, and it tells us, oh, an error occurred, and maybe that's a better simulation. But really, what we're getting here is not a correct simulation of what we wanted using floating point computation. And if we were to think about global optimization, that's kind of a similar type of approach, where we've got this infinite process that we have to finitize, of course, which is why we have this convergence criteria up to epsilon. But with floating point, we're not really finitizing. We can't finitize it to any particular point. So that's really the problem with floating point here. We always have to pick a point where we have a cutoff, just because of the sort of granularity of floating point. So these errors that we experience, often they're unimportant, but sometimes they're crucial. And in this situation, they're crucial. And floating point has a very high level of precision, as does double and all sort of types that come out of that. But this granularity is fixed. And everyone knows that this granularity kind of gets more severe around 0, and then the distance between numbers increases as you go along the number line, which is very good for performing these sorts of computations. But it's still fixed. The granularity still has a fixed level. We can't change it. And so in this way, floating point can be thought of as a discrete data type. And this affects both continuity and convergence. So if we're estimating the continuity, we're going to get to a point where we can't go any further. And the same with convergence criteria for global optimization. We're going to get to a point where we can't decrease the epsilon any further, because we've literally hit the maximum possible value of the distance between floating points. And then all sorts of wonky things happen where you can't estimate the bounding process any better. And this breaks the three criteria that we had earlier. So this is not, we can't define global optimization to be convergent in this way. It can't be guaranteed using floating point. So what we require is not a discrete data type, but instead what we would think of as kind of like a continuous data type for arbitrary precision real numbers. And this is what we call constructive reals. And I said earlier that some people may convince themselves in certain situations, okay, well, we can just come up with various techniques to get around these problems with floating point. But what I'm trying to convince you here is that in this situation, floating point just is unsuitable. We really do need to kind of throw the baby out with the bathwater. You can't like get around the problem that you have here. And so what we're going to do now is kind of introduce these constructive reals, which some of you will be very aware of and some of you won't have used before. So what are constructive reals? I mean, there's various different ways that we can describe them or define them. So one way of defining them is that all the real numbers that can be constructively located by two rational numbers. So if you have two rational numbers, you can say, well, this particular real number is above the left-hand rational number or below the right-hand rational number. And we can do this iteratively to kind of locate where the number is on the real line. These are constructive reals because you can do this using a finite process on a computer. So if we think more about algorithms, constructive reals are those reals that can be reconstructed by an algorithm to any degree of precision. Again, saying any degree of precision, it's this whole, we have an infinite process, we're finitizing it. We can go further, but it still works on a computer, of course, because we're finitizing it. And this is what Alan Turing talked about when he originally introduced computable numbers. He kind of had a system with a Turing machine. So we could, for example, represent all real numbers as like an integer with no decimal part, and then some sort of Turing machine with an infinite tape where at every point we can see the decimal digit. So at any point n, that's the nth decimal digit of x. So this is one sort of example way that you could have constructive reals defined as a data type. Another way is you could have functions from integers to integers, where you kind of give an input level of precision, and then you get some sort of output large integer that represents where to that level of precision you are on the real line. And if you build this function satisfying this kind of condition where you say, okay, well, the code we get out multiplied by, well, it doesn't have to be 2 to the n, but we pick 2 to the n. The distance between that and the actual real number you're representing is always going to be less than the precision at a lower level. And so what it means is that you're never too far away from, at that level of precision, you're never too far away from the actual number you're representing. And this is exactly the same as just locating the number. You know, all these processes are identical, they're just done in different ways with different data types. And so how can we describe these three processes in a clear way? And I think the clearest way to describe this is it's a continuous data type. It's a continuous data type where the granularity of the line is dynamic. So rather than with floating point where the granularity is fixed, it's very high, it's very good, and it's useful in many circumstances, but it's fixed. Whereas here we can always say, well, we want it a bit better, we want it a bit better, we want it a bit better. And in the infinite, this converges to the real line itself, because obviously the distance between these numbers is going to become infinitesimally small at this sort of infinite level of precision. So I'm going to look at two different sort of implementations of constructive real numbers, which relate to the ones that we introduced here. So it relates to this one and to this one. So the first one is implementing constructive real numbers as signed digit sequences. And this is used to represent numbers in compact intervals. So if we think of a compact interval minus n, so we could have, I don't know, minus 64, 64, or perhaps more simply minus 1, 1. These can just be represented as infinite sequences, just like with the Turing machine example. But we're not going to limit ourselves to decimal numbers here. And so because we're not limiting ourselves to that, we have to have some sort of procedure for working out what number we're representing. So this is obviously an infinite sum. And okay, you may not want to work this out on the fly, so I'll try and show an example. So if we're representing numbers in minus 1, 1, the unit interval, then we just use 3 digits. We just use minus 1, 0, and 1. And so if we have the whole line, well, we can represent minus 1 with an infinite number of minus 1s. So this here is the number that's being represented. This here is the representation, or the code. So this is the code, and this is the number that's being represented. So this is like what you would have on your machine, and this is like ideally what you would have. So in floating point, this would be like a binary, 64 binary digits or whatever, and this would be the number that you print out. And that's the same thing we're doing here. The codes are just streams in this example. So if we represent 1, that's an infinite number of 1s. And these are the only ways of representing the endpoints. Representing 0, we have an infinite number of ways of representing it. I mean, the most natural is an infinite number of zeros, but we could also do 1 and then an infinite number of 1s, or minus 1 and then an infinite number of 1s. We can do various different things like this. And every other number has an infinite number of representations, which is perhaps something that is not as helpful as in other situations, but we can see that we can still do plenty of things on this. So for example, if we want to represent any number in this line, basically we have a choice at any point. Do we want to represent something in the interval to the left? Do we want to represent something in the interval to the right? Or do we want to sort of represent something in this middle interval? So if I choose to go left, so I have a minus 1 as my first digit of my infinite stream, then all the numbers represented with a minus 1 at the start are going to be in this left-hand interval now. So I can still represent 0, as I said. It's a minus 1 followed by an infinite number of 1s, which you can see here. We've gone minus 1. But now if I go 1 an infinite number of times, I'm going to get to 0. And the center of this interval is minus 0.5. And what I mean by the center is basically like, if we put an infinite number of zeros after this, then we would obviously hone in on the center of this interval. So that's a nice way of kind of truncating this infinite process. Again, finitizing an infinite process. Now I'll zoom in a little bit to where I am, and now I can only represent numbers in this. So I can't represent 0 anymore. There's no way for me to represent 0 if with a stream that starts like this. Maybe I go right and then left, and now I get this number here. And maybe at this point I'm happy, I want to represent that number. And so what I can do is just, as I say, truncate it, add an infinite number of zeros, and that gives me the representation of that particular number. And again, this is the locating process I was talking about. You go left, you go right, you go middle, and then in the infinite, you get to a particular point on the real line. And so this truncation process is what gives us the dynamic granularity that we were talking about. Because if we truncate to 0 digits, so we just have an infinite number of zeros, nothing else, then we only get sort of 1 point on the line that represents everything. If we truncate at 1 digit, then we have 3 different representations, a -1 followed by an infinite number of zeros, a 0 followed by an infinite number of zeros, and a 1 followed by an infinite number of zeros. And these are the specific numbers that those would represent, and the intervals that those would represent. So now at sort of precision level 1, if you like, we get 3 different candidates. And then at precision level 2, we have 7 different candidates. Now there's 7 intervals in the line that we can represent. And this keeps increasing until eventually we get back to it, we recover the real line. And that's what I meant by a dynamic granularity that converges to the real line. Because at every point you're making a choice to go right or left or right or left. And in the infinite, you get to a point on the real line. This type, as I said, it has an infinite number of representations for every number, and so it can seem a bit unwieldy to work with. But we actually have defined, not in my work, but in previous work, it's been defined continuous functions for negation, the midpoint, infinitary midpoint, truncated addition. Obviously, it's truncated because we're in compact intervals, and multiplication. So we can actually perform arithmetic on this particular representation, which is really nice because then we can kind of have fun with constructive reals in this way. And I talked earlier about modulus of continuity, and these are continuous functions. And in this regard, what the modulus of continuity tells you is, okay, say I've performed an operation like x midpoint y, and I want to find that out to say 7 digits of output. How many digits did I need to know x and y to? Maybe I need to know them to like n plus 2. So like if I want 5 digits out, I need to know them 7 digits in, for example. And that's what the continuity means in this regard. And that's what allows us to compute this basically, because we know we only have to do a finite amount of computation to work out a finite amount of computation out. Again, it's the finitizing this infinite process, and that's what allows us to perform this on the computer, of course, rather than having this discrete way of doing it as in floating points. So this data type is great. It's really interesting, but it's a little bit unwieldy to work with sometimes. And you can't really define very interesting examples because we're working on these compact intervals. So even addition, it's truncated, and we have to do a lot of casting around in certain areas if we want to use different intervals. And so we want a way of performing sort of constructive arithmetic in a much nicer way. And the way that we can use is called Boehm encodings for real numbers. So Hans J. Boehm, he developed this framework for exact real numbers in Java in the late 90s, and recently it's become the basis. He works at Google now. It's become the basis of the Google calculator. So your Android calculator uses these real numbers behind the hood, which some people don't know about. But you can muck around on the calculator yourself and test things out. And you can see, for example, if you do some complicated expression that requires comparison to 0, well, comparison to 0 is not decidable with an exact real number. And so in some certain situations on that calculator, your calculator will actually time out. Whereas on another app that uses just floating point, it won't. But it won't give you a correct result in those cases. So how do these Boehm encodings work? So a real number x is represented as an object. The real number is brackets x. So x is the sort of object that represents it, which has a method where it takes an integer. This is the level of precision, as I said earlier, and it gives back a big integer. So these are both types in the JDK, as you know, and it satisfies this equation that we saw earlier. So the distance between 2n times the encoding of that number at that precision level, the distance between that and the actual number being represented is always less than the width of the precision at the next level. So the error is, you're never too far away from a number that you're actually representing. But I can't really describe this in like a textual way because it just looks confusing. Like the approximation of pi to level -1 is 6, and the approximation of pi to level -5 is 101, and this means nothing like at this point. And the approximation of 3 to level -1 is also 6 as well as pi. So how can we tell that this is 3 and this is pi? So it's better to just try and illustrate this. But what we're saying here is, again, the precision level, which is the n, the argument of this function, that is what's used to dynamically specify the granularity. And so what we have here, so if we have a real line, at any level n, the width of each representational interval is going to be 2 to the n. That's what this inequation sort of, this inequality kind of realizes. So what I mean by that is at level 0, so when the argument to this function is 0, all of these intervals are of width 1. And the center point is exactly the center points of the integers, which is great. So we can represent the integers using this. So down here are the numbers actually being represented, and up here are the encodings. So if we approximate 0 to level 0, we get back 0. But if we approximate 0.4 to level 0, we also get 0. So we're approximating to this particular level, and all the numbers in that interval are going to give back the same encoding. And then if we want to find out where we are in that interval, we have to go to the next level of precision, and that's what is this infinite process being finitized. So if we go to the next level of precision, we see that the splitting is not quite as nice as it was on the streams, because if you fix your eyes directly on the middle interval here, you see when it splits, it kind of splits into 3, and there's a bit of overlap between them. But so that's one drawback compared to the other representation. But one advantage is that we kind of have this real line without much overlap as we had with the previous one. So at this precision level, -1, now all the intervals are size 1/2. And now, so say we were representing 0.4, which would be around here. Okay, this is still going to give back 0. But earlier, if we were representing, 0.4 will be here, sorry, so that will now give back 1. Yeah, so at 0, 0.4 gave 0, but now it gives 1. And so we're locating it on the line. And it's the same with pi. So as I said, pi approx -1. Okay, well, let's look, where will pi be? It'll be around here. And so it gives back 6. And 3 also gives back 6 because it's still in this interval. So these encodings are what are used at each level of precision to locate these numbers. And I won't show you the line at precision level -5, but basically between 0 and pi, you're going to have 101 different options, and 101 is the closest to pi. And then at the next level, you're going to have double the amount and double the amount and double the amount. And what's great here as well is we don't have to just use compact intervals. Because we're using integer, we can keep going in either direction. We get the whole real line centered at 0. So as the level decreases, again, the width of these intervals is going to decrease further and further. We're going to get it to 0, and now we're representing just the actual real number. And so we choose a precision level at any point, and we can use the continuity to do this on certain operations. And that's what allows us to infinitize this process and use this as a data type for the calculator, for example. So there are defined continuous functions for all the operations one would expect for a mathematical calculator. As I said, it's used in that app. And if we try and compute pi to 4,187 places, you can do that in this, and you probably couldn't do that in floating point, or at least more complex calculations you couldn't. Okay, and we can easily define modulus of continuity functions on these operations, just like how we could for the stream representation, which basically tells us what level of precision do I need to go to. So for addition, for example, in this library, you need to go, I think, 2 levels lower, sorry, approximation. So if you want to compute x plus y to level -3, for example, you've got to compute x to level -5 and y to level -5. This is still all finite, and so you can do this. So I want to get back to our global optimization I was talking about. So what I've done is I've kind of built an implementation of this branch and bound process in Java for these Bohm encodings. I'm not going to show an actual run. So this is an actual run of the algorithm, but it's given pictographically rather than showing you it in Java, which would, it would all go wrong. So if we try and we just give a basic one-dimensional function, and we set the epsilon to 0.01. So once our total height is below 0.01, we can return the entire candidate space, and that's a given candidate. That's the given space of where we say, okay, the global minimum, we've zoned in on this area. So let's start with interval, I don't know, -3 to 3, and this is what this function looks like from there. And the modulus of continuity now is going to bound this process, yeah, and it bounds it at a ridiculous height. So we can see it only goes up to about 900, but it's going to bound it to 16,000 odd, and that's because this function increases so quickly that the modulus of continuity that we've got doesn't estimate it that well. And we can, you know, one thing to make these algorithms better is to improve the heuristics, not the heuristics, sorry, but the working out of these bounding processes using the continuity. So at the start, we have this huge interval, but very quickly, after just a few sort of branching and bounding, we've completely zoned in on this interval now, which is where we know that our 2 local minima and our 1 global minima lie. This interval is given here, and our bounding now is -4 to 4. So it's still a big overestimate, but it's better. And then just a few splits later, we're sort of getting a bit closer, and now we're only estimating the minimum function lies in -2,2. And then at the next step, we've got rid of this local minimum completely. So we've only got 62 candidate intervals now, but they're all in this space. Yeah, so we've got 62 different points that are being looked at here, all at different precision levels, because, as I say, we can have dynamic precision here, and they're all estimating the function, and that's what's giving us this total space here. And then very, very quickly now we zoom in on this area, because clearly it's just the best area. And we discard loads of intervals in the way that I showed earlier, where it discards an interval if it finds something that's completely better than it. And now we focused in on this area very quickly, and we focus in even quicker. And now this process is just going to, you know, if we don't set the epsilon as everything, it's just going to keep zooming in on this, and eventually it's going to have thousands and thousands and thousands of candidates in a very small area. So we get to a point where it has 315 candidates, all in this area, and now the distance here is less than epsilon, so we can return this. So now we can return this interval as the global minimum is somewhere here. And if we want, we could just use a local process now to give us an exact number back. But we can actually represent this as an exact real number, or like the nearest interval bigger than it as well, and we could return that if we want to. So that's how this global optimization, this branch and bound approach works using these encodings. We can see how very quickly we've got this convergent global optimization working. It's only for 1-dimensional here. We can extend it to multiple dimensions though. And so now what I want to talk about is how we've applied this kind of work to the foundations of regression analysis. So we've looked at global optimization and how that's convergent, and how we can use constructive reals to give us proper algorithms for convergent global optimization. But now I want to talk about how we can apply that to the field of regression. And what we want to do here is we don't just want to focus on data types, that sort of predefined data types. We want to look at what's the most general data types that we can perform this regression process on. And it turns out that these types are called searchable. This is work done by Martin Escardo. A data type's called searchable if we can construct a search algorithm that, given a predicate, so we ask it some sort of question, it returns an element of that type that satisfies the predicate, if such an element exists. So for example, you know, if we looked at all the numbers between 1 and 10 and said give us back an even number, okay, well it can do that, so it will return the first even number it finds. If we said give us back 11, then it's just going to return something bogus, but we know that such an element doesn't exist, so that's fine. And obviously every finite type is trivially searchable, because we can just look at every type and we know that that's going to compute in a finite time. But what's perhaps interesting, although I hope that this talk has shown why this is the case, is that some of these kind of dynamic infinite types are searchable on, not on all predicates, but on certain predicates. And 2 of these types are the ones that I've shown for exact real arithmetic, for constructive reals, because we've got this dynamic process. And these predicates, we call them continuous if they can be knowingly answered with a given limit on the granularity of these types. And that's what I was saying about these functions being continuous. You know, if we want to add two numbers up to decimal point 7, then we need to look at the two arguments to decimal point 9. Well, that is what gives us this granularity process, and that's what allows us to do the same with predicates. And then that essentially allows us to search these types as if they were finite. And these types are all exactly the ones that we can define this convergent global optimization on, because what we can do is the predicate is find the global minimum up to this epsilon, and that's a continuous predicate because we know there's a limit using the continuity of that function. We know there's a limit of granularity we have to go up to, and now this is essentially a finite process. But the way it's done is in this dynamic way, which means that we're not just looking at every single point, but we're searching it in a clever way. And once we've done this, we can build even cleverer ways of searching this while not getting rid of our correctness proofs. So I'm going to talk about function approximation. And in function approximation, what we want to do is reconstruct some function from some data observations. So this is the classic supervised machine learning situation. We have some data points x and y, and we want to fit a curve to it. And these data observations can be thought of in a functional way as coming from some sort of true function, some sort of data oracle, right? And we've just plucked a few examples out of it. And we can pluck more examples if we want or not. And this oracle is usually assumed to have some sort of observation errors. And then, you know, in normal regression, you would like reduce the least squares error or whatever. So the goal in function approximation is to minimize the loss between the function that you're reconstructing and the data oracle. So this loss could be some sort of least squared function where you say, okay, well, I'm going to look at these particular points and I want to minimize the least squared error. And you can define this as some sort of interpolated data oracle between the data observations and do exactly that. The reason I'm introducing this is because I just want to give this sort of functional approach of what supervised machine learning sort of asks in general, for general types. And what it says is reconstruct a function from x to y, using from some data oracle that's also from x to y, and minimize some sort of loss process that gives you back some loss in the real space or some representation of a real space. Or we could use some other type here for error, but we'll use the reals just to make it clear. And clearly, based on what we've already said, a function approximation process is convergent if for any epsilon we can minimize the loss below epsilon. And we can sort of start to see now the connections between this and the global optimization. So we've got a global optimization, which we've already discussed, and now we're talking about function approximation, which is sort of more applied machine learning, and we're starting to see the connections between these two areas. So again, as I said, it's convergent if for any epsilon we can minimize the loss between the reconstructed function and the oracle function. And I'm going to explain two different function approximation processes, the ones I briefly touched on at the start, and they're interpolation and regression. So interpolation, this is the process where you get a load of points, and as I said, you join the dots or you fit a curve. And this is curve fitting via interpolation, and the more points that you have, and there's certain requirements about how you pick these points and how you fit them, but the convergence of this has been well studied. This converges to any epsilon. As long as you pick the points in a good way and as long as you fit the curve in a particular way, this is guaranteed to converge. The convergence of regression, however, has not been studied as much, it seems. And this might be because regression depends on sort of an additional parameter, which is the model function. So what regression is if we think of parametric regression, is you have some sort of function that you want to reconstruct, that you want to fit a curve to. What you have to decide in advance of regression is some kind of model function, which depends on some parameters, yeah? So for example, this function, we know that this is a good model function for it because it's the same as the function up to some chosen values of the parameters. We know that there exists some parameters that are going to perfectly fit this. And if you choose the wrong loss, you're just going to get something that doesn't work completely. So the convergence of regression really depends on a correct choice or a suitable choice of model function. So for us, this is the model function that we've got. So the function that we're trying to construct is of type x to y, as we can see, r to r. And then the parameter type is r to the 3. We have 3 different parameters that we're trying to tune. And given the epsilon, that's going to tell us to what degree we need to tune them. So if we had a rather big epsilon, perhaps 0, 0, 0 would be fine. We can just return that. That's a good curve fit if you've got a very high epsilon. And maybe this is a better curve fit because it fits in all this area, but then it goes off. Maybe this is a better curve fit if you have a slightly lower epsilon. And this is actually a pretty reasonable curve fit if your epsilon's not too small. But obviously we know we can minimize that epsilon to any degree of precision. And so what we're doing here is we're searching for the best values of this function. We're minimizing this loss function, which we take 3 arguments, and then we want to minimize the loss between those arguments plugged into our model function that we've decided in advance and the true oracle function, which I told you what it was earlier. And so what this is it's just global optimization. We're just minimizing these 3 arguments, and that's all we're doing here. So we can find these arguments using a branch and bound process, for example. And so what we've done now is we've reduced regression to parametric regression to global optimization. And so what we're saying here, what our program's saying is that we can kind of get this convergence criteria out of regression from the convergence criteria of global optimization and a few different things like you have to choose the model function correctly. And so convergent regression is just convergent global optimization. And that's the area that I'm currently studying. And I want to extend this algorithm for global optimization to one for regression, so that you can kind of find these parameters given, obviously you'll have to give certain starting compact intervals and stuff like that, but it would be great to have a kind of system that finds these parameters for functions and guides the process in some certain way. So that's kind of what I've been looking at recently. So I'm going to conclude the talk now. I feel like I've set up quite a large area for discussion. But what I want to try and conclude by saying is that throughout this talk, what I've tried to outline is that there's been huge investment in local optimization algorithms via gradient descent. And we can understand why. The applications to deep learning are enormous. There's loads of fantastic efficient algorithms and dedicated hardware for local optimization, gradient descent. But sometimes finding the best solution to a problem, I might mute it for some reason. Oh, I stepped on my mute button, sorry. So sometimes finding the best solution is crucially important. And further sort of improvements to local optimization are not going to somehow get us to global optimization. And this is why I said, like, sometimes we have to throw the baby out with the bathwater. And so what I've tried to introduce here is a different line of work, which some of you won't be familiar with, which is not just global optimization, but convergent global optimization, and not just that, but on using constructive real numbers. And because what I've also tried to say is that floating point numbers are unsuitable for this. What we need are dedicated types, and it would be great as well if we had dedicated hardware for constructive real numbers, which allows us to perform this kind of convergent global optimization. And we've seen how we can apply this to situations that are already very important to machine learning, like regression, for instance. So I think this line of work has promise. The theoretical guarantees can be established mathematically and applied to these foundational questions such as convergent regression, which, yeah, that's interesting from a mathematical point of view, but additionally, it can be interesting from an actual algorithmic point of view of machine learning, because we know now that in these particular situations, we never get an incorrect result. And admittedly, the algorithms require a lot of work, as they did with local optimization in the late 90s. But I think this work could be worthwhile. And so I hope that I've introduced this area reasonably. And if you have any questions, then I'll answer them now, or I'll try to answer them now.